Day 122, lenses and how they form images with ray diagrams. A lens is a transparent material, it's usually glass or plastic, used to bend or refract or focus light. Lenses generally are not very useful unless they are thin. They can be thick, but generally the thinner they are, the better they work. They function similar to mirrors. We use some of the same, or basically all the same terminologies we use for mirrors, except for they refract light instead of reflect it. We want the light to pass through the lenses and not bounce off them like they do with mirrors. Just like with mirrors, there's two types. There's the converging and the diverging. The converging causes light to come together at a point we call the focal point. We label that with a capital F, just like with mirrors. From the side view, these lenses are thicker in the middle. These are the types of lenses people use to correct farsightedness. In other words, people who can see far but not near, they need these glasses to help them see near. A lot of times reading glasses for people in their 50s or 60s, this is the kind of lens they have. Sometimes they're called magnifiers. They help people to correct and see things near if they have difficulty with that. As opposed to the diverging lenses, which, like diverging mirrors, they cause light to bend apart. And they're, as you see in the second diagram here, the focal point is what we call a virtual focal point. You have to extend backwards, project the refracted rays backwards to find that virtual focal point because the light diverges. These lenses are thinner in the middle. They help correct for nearsightedness. Most people who wear glasses, at least when you're younger, have this type of lens. When you get older, you have a combination of diverging and converging. They're called bifocals. You need both types of lenses because you have trouble seeing far and near, possibly. But most people who have glasses have this kind of lens to help them to see far, to focus on things far away because you have trouble doing that. Now, capital F is called the focal point. And if we measure, however, from the center of a lens, any lens, to the focal point, we call it the focal length. As you see here, that's measured in meters, centimeters, but meters would be the standard. But we call that little f. Little f is the focal length, measured in meters. And for a diverging lens, I'll highlight it, you measure between those two blue spots, the middle of the lens, along that horizontal principal axis, to the focal point. With the diverging lens, it's called the virtual focal point. That would be the focal length. Once again, we'll usually use centimeters, but the standard would be meters. Now for a converging lens, f is positive. For a diverging lens, f is negative because you're measuring backwards for that virtual focal point. Keep that in mind when we do the lab. Here's some more profiles or side views of different types of converging and diverging lenses. It won't be that important. We'll usually draw diverging lenses as this first one, this double convex lens here. But all three of these are converging lenses. You can see how they're thicker in the middle. They would cause light to converge, just like the diagrams you showed at the top on the first slide. And this second set here, these are all diverging lenses. It also turns out, as you'll see in the labs here in a few minutes, or the examples, that lenses actually can work both ways. They actually have two focal points. You can go from left to right or right to left. I'll show you that in the example. So as with mirrors, lenses can form images with light that passes through them. An image is an optical appearance using the mirror or the lens. Like we mentioned with mirrors, there are real images caused by actual light converging. These images are always flipped upside down if your object is right side up. And we can measure the object distance from the lens. We use this lowercase p to measure this distance. I'll show you an example in a minute here. And then the virtual images, which are formed by light that only appears to converge. Flat mirrors always do this, but now we're talking about lenses, and we'll show you some examples. But virtual images, like with mirrors, the virtual images are always upright, not flipped. When we measure these with a ruler, we're going to refer to this measurement with a lowercase q along the principal axis. There is an equation that we will be using that forms a relationship between all these quantities. And once again, I'll write the equation down right now, but then I'll explain it with the examples. And that is 1 over F equals 1 over P plus 1 over Q. Well, those are all lowercase. These are all measurements in meters or centimeters, as long as you're consistent. Let me show you how that works here. Using ray diagrams to explain how lenses form images. Once again, the challenge is that we have a two-dimensional piece of paper on which we're trying to explain a three-dimensional world. Now, in real life, images are formed by millions of rays of light from every point on the object. We found that really 2 or 3, well, I'll show you 3 here, but you really only need 2 of these 3 to illustrate where an image is formed and how it's formed. For example, we have this lens indicated in red here on this diagram with the principal axis, the horizontal line, and the focal points of the lens. We did the labs where we found focal points. Let me just highlight them on the diagram here. There's a focal point here and here. I'll make red dots. Right? Turns out that lenses have focal points on both sides. If you shine the light either way, you get an equal focal point on either side of the lens, equidistant from the lens. On many diagrams, there'll be a second spot, and they use a C here. Let me use a blue dot. I'm going to call that 2F. Most books will call that 2F, twice the focal length. That dot right there is twice as far from the center of the lens, which I'll indicate with a blue dot, as the focal point. And the same thing on the other side. Everything is symmetrical over here. Let's call that 2F instead of C. That's twice the focal length. That's that spot right there on either side of the lens. Anyway, if we have an object, in this case the object is an arrow, but let me turn it into a candle. It doesn't have to be a luminous object, but I'm going to make it into a candle. So the candle has a flame that gives off light, but it has to be something that gives off light or reflects light. In this case, it's a candle giving off light. And there's light that goes in all different directions. There's light coming off from this candle in this direction, in this direction, in this direction. I don't care about any of that light. I could draw these all day long, millions in all different directions, but none of those hit the lens. So in a real problem, I'll never draw those 4. In fact, you might not need to draw them right now. You don't need to draw them right now, but what you do need to draw, or it's already drawn for you, is this example number 1, a ray of light that goes in parallel to the principal axis, the horizontal line cutting through 2F, F, the center of the lens, horizontally through that lens. So that ray I just drew, highlighted, is horizontal. It's a ray that passes parallel. It's a ray from the object, parallel to the principal axis. It refracts through the focal point, or the focal point on the other side. In other words, it goes through the lens, and by the way, when it goes through the lens, it actually bends twice. It bends when it goes in, and it bends when it comes out. We're not going to get that picky right here. It bends. The net result is it bends and comes like this and continues on. That's one ray of light that helps us find the image. Step number 2, I'm going to call that number 1. You don't need to number these, but that was my number 1 on the illustration here. Number 2 is just the reverse of that. It's a ray of light out of millions I can draw, but that goes through a focal point. I'm highlighting it down here now. It's a ray of light going through the focal point on the left-hand side. It hits the lens, bends twice, and that result is a ray of light continues on like that, parallel to the principal axis. That's number 2. So it's just the opposite of number 1. A ray passing through the focal point will refract parallel to the principal axis. And finally here, I will do this one in blue. It's already in blue, but I'll highlight it again. Ray number 3. It's a ray of light from the object. And I always start with the top of the object, whether it's a burning candle, or a cat, or a dog, or a person, or an arrow, or a tree. Start from the top of the object. All 3 of these start from the top of the object, showing you 3 rays of light that would be bent. Now, it turns out that the one that goes through the center of the lens is essentially unbent, undeviated, unrefracted. It's not really a word, but it goes through the lens. There is a slight bending, but the net result is there's very little significant bending. I'm going to call that number 3. I'll use blue. That's ray number 3, technique number 3. So there's three basic rays that we can use to find an image. And if we're lucky, they all intersect at one spot. Sometimes they're not perfect. In fact, in the lab, you'll find out it's not perfect. But you do your best approximation of where they're coming together. And that really defines the top part of our image. In this case, if it's a candle, that red dot that I just drew over there will be the flame of the candle. And I can repeat this process for the middle of the candle with light that's reflected off the waxy part of the candle, and it would map. I'm not going to go through the three steps again, but if you did, say I took the middle of the candle, I'm using a black dot on the object over here, and if I repeated this process with the same three techniques, three specific rays, that point right there in black on the object would map over to this spot on the image. And I could keep repeating this for any point on the object. It would map over to a corresponding spot on the image. But you really only need to take this diagram like I've done it so far with the top of the object, map it to where the top of the image would be, and then you can draw the image. The image would look something like this. In this case, it's always based on the principal axis, but it will be upside down. So this that I'm drawing right here is the image, this red, and I'll kind of fill it in a little bit. The candle will be upside down. There will be a flame over here, and that's going to be the image of the object. And that's a real image because it's flipped. As we've mentioned before, real images are flipped. They're upside down. We'll give you some more examples of that in class. But I also want to apply these principles to diverging lenses. Let me go to the next slide. Here's a diverging lens on which we're going to apply the three principal rays to locate our image. So here our object is a pencil, and as you see, they start from the tip of the pencil. Whatever your object is, a pencil, a cat, a bunny, a Tyrannosaurus Rex, whatever you have, start from the top of that object and draw your three basic rays. Now, this one follows the three same principles, but be careful here, and we'll practice this in class as well. I'll do this with blue. So I'm starting at the tip of the pencil every time. Ray number one is a ray that comes in parallel to the principal axis. Once again, it bends as it goes in and it bends as it comes out, but they're showing one bend in the middle of this lens, which is okay. The net result is the ray comes out like this. That ray is bent, that light is bent. I should have mentioned once again that this lens, like the previous lens or like any lens, has two focal points. It has the one over here that we measured in class, technically a negative focal length from the lens to that focal point, and another one equidistant on the other side. Both of those red dots I'm drawing, labeled capital F for focal point, are the same distance from the center of the lens, which is this blue dot that I'm highlighting, dead center of the lens right now, on that principal axis, that horizontal line through the entire diagram. Anyway, so once again, this top ray, rule number one is the ray comes in parallel and it's refracted out such that, I'm going to call that number one, its backwards projection, okay, that actual blue highlight that I just did there is actual light. That's solid. As we did in the lab, always draw the actual light solid. Anything that's not actual light, that's going backwards or drawing normal lines, always draw those dashed. So what you see there, and I'll stick with the red, is a backwards projection that's lined up with our focal point. All right. Rule number two, all right, is the reverse of rule number one, but here's where we got to be really careful. The ray of light leaving the pencil is going toward the focal point on the right-hand side of this lens. Once again, I'm using an arrow to show you how light is traveling. It doesn't go straight through. Yes, it bends twice, but the net result is it bends parallel to the principal axis. Rule number two is the opposite of rule number one, but we're using the other focal point. In other words, that ray of light would have, if I continued, it would have gone all the way to the F on the right-hand side. I will highlight that with red again. It goes like that. That's not really going to be important right now, but that's how you get that part of the problem started. And in the third case, and this is usually the easiest one to draw, sometimes students start there, if you have a ray of light that starts from the pencil tip, or the top of our object, it goes through the center of the lens and it never bends, or the amount of bending is insignificant. That's rule number three. So those three diverging rays, because that's what diverging lenses do, they make the light diverge, they're not intersecting over here on the right. You have to project them backwards, those three, backwards. I'll circle them in black again. Numbers 1, numbers 2, and numbers 3. I have to take those three and project them backwards, and now I will do it in black. All right, so they go backwards, and where they intersect, that's where the image is. All right, now the one through the center is its own backwards projection, but they all, once again, if you're lucky, they all intersect in one spot. I'll highlight that in blue, in black, that black dot. That black dot is the image position of the top of the image, the tip of the pencil. So you see, we have the image here. The image is always based on the principal axis. So we have a small pencil here. If you draw the image, it's already drawn for you, which is smaller than the object, and it's a little bit closer to the lens than the object is, but it's a virtual image. It's upright. So that's virtual. And it's smaller than the object. So that's how diverging lenses work in their formation of images.